All right, everybody. Quick reminder about the 4 reactions involving water. Not on this screen, but earlier we did hydration of alkenes to make alcohols, chapter 6. And then we just learned in chapter 10, you can take the alcohol that you made and dehydrate it. The opposite of hydration being dehydration. And hydrolysis is a reaction where you use water to break a molecule apart. Use water to break a molecule down to 2 smaller molecules. What's that the opposite of? No. Condensation. If I bring these 2 molecules together to make this molecule, I will also make water. That's called condensation. I bring these 2 molecules together to make a bigger molecule. I'm not going to write that down. It's the exact opposite of what's hydrolysis. Bringing 2 molecules together to make a bigger molecule and water. The hydrolysis used the water to break a big molecule down to 2 molecules. There you go. You are not responsible for any hydrolysis mechanisms till Chem 242. No hydrolysis mechanisms till 242. And of course, when we hit chapter 11, I may change my mind, but I don't think I will. There's hydrolysis of ethers, but I think we're going to skip it. But condensation's big. Hope it's clear. Oh, there you go. I already had that statement about the Chem 242, but I didn't say Chem 242. So here we're clearly bringing 2 molecules together in the presence of a catalyst, in this case sulfuric acid, to make a large molecule called a chromate ester and water, the small molecule. And then we get a new step called oxidation. And there's typo. I think I corrected your typo on your sheet. I wrote it by hand, but I didn't correct my original. Okay. So I need to bring this O to the chromium. You'd think maybe it just attacks it, right? Problem is, this is a lousy or a poor nucleophile. We have to learn that for next Monday anyway. That's an alcohol, right? The poor nucleophiles have a neutral oxygen in their structure. So this one does not want to attack chromium. The first step is to make the chromium more attractive to it. It's called activation. You don't need to know this word. How do you activate the chromium? By protonating an adjacent oxygen. And you pick one that has the double bond, please. Don't pick one that has the single bond. If you do that, then the product you make can't resonate, which means you picked the wrong one. This is the right one because this product you just made can resonate with the other O's. Okay? So now the poor nucleophile is reactive enough to attack chromium. And you have to break one of the bonds. Which of those oxygens is pulling the electrons most strongly? If you have a plus charge, you're pulling electrons very strongly. You're going to neutralize the O this way. And you're going to get this species here. Didn't want to go through my molecule there. So we got our isohexyl, isohexyl. Sorry, 1, 2, 3, 4, 5, 6. It's sec and iso, that's why I was having trouble. This is now attached to a chromium that has an OH on the bottom, an OH to the right, double O on top, OH to the left, and that is an oxonium. I'll take a guess for what you think happens next. I got a hint. Leaving group. She said make a good leaving group. You do see I need CO chromium, and this needs to be neutral, right? CO chromium, that's an oxonium. So tell me how I can quickly get to the CO chromium without an oxonium. Take away the H using the conjugate base of your catalyst, which means you are regenerating your catalyst for further use. We're going upstairs because we're almost there. The synthesis portion's done. Double. Free keyboard just showed up out of nowhere. Why do you think I colored those in a weird way? Because we've done the synthesis portion, what's left? Remember I said the biologists always name it backwards? Yeah, this is dehydration step. You see the water there is the other product? It's black. Make water leave. You got to strip off the black H and then the black OH. What's going to take this H? This is dehydration, by the way. Dehydration step. You ready? Think when doing the dehydration. Use similar arrows to the big T word. Remember the big T word? Tautomerization. So you're going to need an acid-base pair. Same acid-base pair you've used once already. What are they? We used acid to activate the carbonyl. Chromonyl, I should have said. It's a chromonyl when it's Cr double bond to O. We used a sulfuric acid to protonate it, and we used its conjugate base to deprotonate this oxonium. That's your conjugate pair. The base does the same thing. It deprotonates something. And the acid does the same thing. It protonates something. Base. Acid. Why do you think I drew the acid near the OH? Because it needs to do what? Leave. Are OHs good leaving groups? No. What do you have to do to them first? Make it a good leaving group by protonating it. So you're going to have that as part of your mechanism. And you're going to have the base grab this H. And I'm going to tell you something. These words are great. Until you feel these words, you're not really there with your mechanisms yet. You've got to look at these mechanisms beside each other. Find any tautomerization we've done in the past with sulfuric acid and hydrogen sulfate. Copy the mechanism. Copy this mechanism right beside it. Look at them side by side until this sentence makes a little bit of sense to you. If it never makes sense to you, you're going to be struggling. When I tell you a reaction is similar to another reaction, please study them together. I'm trying to help you, okay? So, use similar arrows to tautomerization. And you have successfully stripped water off of this thing. And you made a new chromium double bond to O. And this is called a chromate ester. Esters of chromium are not stable like carboxylic esters. Carboxylic esters will last for thousands of years if you don't give them anything special. This chromate ester ain't going to last but a few seconds. Under these conditions, there's water present. It's going to react with the water that you've actually made in the reaction. And you got to get me from here to here. All the things you need are these two things becoming these three. You don't have to add any other molecule. Tell me what happened to water in this mechanism. You protonated it with one of the H's up here. Which one? The one on the C with the O. Yes, sometimes they're not obvious, are they? But this H does not exist in the product. It gets that H taken off using water. Also, compare to tautomerization. This is like an abbreviated tautomerization. So, hey, when you took the H on the mechanism we just finished, what did you do with the sigma bond to that H? Because you need to do it again here. When you took this H with a base, what did you do with the sigma bond? I made a pi to the adjacent atom in. Please do so again. And you tell me how this becomes HCrO3. It's a lot easier than you think. Just this becomes a lone pair on the CR. So it's a little different there because it ends earlier. But it starts the same, doesn't it? You want Greek letters? Grab H from a beta position. You don't need the Greek letters. If you grab H from beta, you make a double bond to alpha. Grab H from beta, you make a double bond to alpha. Yeah, it's like elimination, right? Alpha, beta, elimination makes alpha, beta. Look at that, I got 3 Greek letters in there. Alpha, beta, pi. That's a pi bond between the alpha and beta position. So we did an elimination there of water. And we did an elimination here of chromous acid. It's a chromous acid. How about a reduced chromium? There you go. So chromic acid oxidation, that's what the overall thing's called. And it comes from chromic acid. And we know how to make chromic acid, believe it or not. Top of the page. Hydrolysis of dichromate in the presence of acid makes chromic acid. We'll talk about that on our next video, but right now I want to make sure you got this.